In today's video, we will talk about something interesting for the Fairbanks Morse 38G A-1/8 two-stroke uniflow scavenged diesel engine, which was designed during the World War II for powering the submarines, but currently still in production as backup power supplies. And the second thing today we will talk about is a power cell I saw in the museum 2 weeks ago on another Fairbanks Morse, but a smaller bore two-stroke diesel engine. And we will talk about something interesting about the turbulence in the combustion process. So the reason for me making this video today is that several days earlier I got this injector, which is for the Fairbanks Morse 38, this diesel engine. It's the genuine part taken down from a scrapped engine, or it's just being changed. I'm not sure, but it also comes together with this unit injector for the Cleveland 278A two-stroke uniflow scavenged engine as well. But this engine is equipped with the exhaust valves and the scavenging ports, but it still takes some time to get the proper tool to dismantle this unit injector, so we will not discuss about that thing today. But it moves freely, and actually I hammered on this side and filled it up with fuel oil, and it actually injects well. So this injector here, I have actually pre-disassembled this one, so we can take a look inside. Well, I will also show you a picture from the maintenance manual from Fairbanks Morse about the construction of this nozzle. So this is actually the spring cage. If I turn this thing here, you could actually see a spring here and some pressure adjusting shims here to adjusting how much this bolt will compress the spring down on its seat. Unluckily, in this injector nozzle here, the injector here, you could actually see there is no push rod acting on the needle valve inside. I believe that the push rod might be lost by somebody already dismantled this thing here. But I actually tested this thing with some pressurized oil, and actually the needle valve and the spray hose are still good. I will show you the spray hose as well in a separated picture. So that let's take a look at this engine here. This is the overall appearance of the engine. In the end of this video, there should be a video of me visiting a submarine engine room, which were equipped with 2 sets of 6-cylinder version of such engines. So let's take a look on its inner construction here. So from its name, you already know that this is a post piston engine, and it has an upper piston and a lower piston. The upper piston is also for the control of the upper ports, which are actually the scavenging ports here. The lower piston also controls the exhaust ports. So one very interesting characteristic of this engine is that from the picture, you could actually see that when the upper piston is on its, I would say, the top dead center. We just call it like that. So the lowest piston actually hasn't reached its dead center here. You could see that it's actually a few degrees from reaching the dead center. So actually this degree is 12 degrees difference between these two cranks. And the reason they do like so, I would say like the first reason could be the time area value needed for the scavenging process, also the exhaust blowdown process. You definitely would need an advanced exhaust timing before the scavenging actually takes place. Also, the second reason is that since we have two cranks here, we need to somehow distribute the load sharing in between these two crankshafts. The first thing I could think about is that we could have different strokes between these two pistons, but they are, how can I say it, like 180 degrees out of phase. That would make a difference in the load sharing. But the second thing you could do is that actually adjusting the phasing between the two piston movement, so that I could say that even if they have a same bore, definitely, because it's the same cylinder liner, same bore, so the same gas pressure acting on two pistons on any time, but you could have a different lever, so you could have a different instant torque in between these two cranks, which gives you a different sharing of the load between the two cranks. So actually, this 12 degrees difference in the timing results in a 28% of power taken down from the upper crank, and the majority part, which is 72% of power developed in the cylinder, is taken out from the lower crank. This is quite reasonable for me because normally we only have that lower crank in a normal engine, and you might make that crank more stronger, heavier, and you could have a much heavier shaft connected to the lower crank. And the upper crank in this certain engine design is actually used for driving scavenging blower and some auxiliary pumps, maybe like the freshwater pump or some other lube oil pumps, like so. So let's move to the fuel injection of this engine, which actually we have seen the fuel injector. So the fuel injector in this liner here, let's see that, does it? Oh yeah, it says the injection nozzle is here, but actually it's equipped with a pair of injectors and a pair of injection pumps per cylinder. So here I will show you a picture of its piston. So from the picture of the piston, which represents the combustion chamber, you could see that actually its shape satisfies the needing for a pair of opposed positioned injectors. So the next thing we will talk about is actually the power cell combustion system. This system is utilized in some of the diesel engines. But before we dive deep into this kind of a combustion system, I will show you a video or several videos I took from the museum for a smaller version of the Fairbanks Morse opposed piston engines.
World War II submarines.
Yeah. They probably had two or
So the engine you just saw is a 5-cylinder version of a uniflow scavenged 2-stroke diesel engine, and each cylinder is equipped with only one injector. Here, these 4 pictures actually, they all show the cross-section view of a cylinder in that engine. So this is a nozzle tip, and in front of it, this nozzle tip, or just opposed from this nozzle tip, is actually the thing called the power cell. So how does it function? It is like that during the injection process, majority of fuel is actually distributed in the main chamber, while a small amount of fuel enters into this power cell. And then the power cell, the fuel gets mixed with the compressed air in this cell and get ignited. But I would suppose that at the same time there should be some combustion already happening in the main chamber as well. So during this ignition, actually some of the unburnt gas in the power cell and the exhaust from the power cell, they shoots back into the main chamber like that. So it causes the strong swirl and turbulence inside the main chamber to get a more uniformly distributed air and fuel distribution and to enhance the combustion. So, but I would say that this is an interesting combustion system, and there is another combustion system which is pioneered by the MAN company from Germany, which is a quite famous M process, or the M type of combustion chamber. So in the upper picture here, this is the chamber located in the piston head, and this is our injector. So during the compression process, and you might notice that there is a leading surface here. This should be the inlet valve gas flow direction. Actually, during the compression process, because the gas is compressed and the momentum is conserved, the angular momentum, the swirl the swirl of the gas flow being compressed inside this chamber will increase, the angular speed will increase and cause a very strong swirl inside this chamber. And then you spray the fuel in mostly the tangent direction of this swirl, and the fuel will be blown and distributed along the chamber's surface. And during the combustion process, this strong swirl still is maintained by its own inertia, and then the ignition, the firing, the combustion all happens while the swirl is still going there. So this causes a very interesting effect, which is that we all know that the lower density material, even it's liquid or gas, will tend to be centered in a swirl because of the centrifugal force, and the more dense material, or the gas we are talking about here, will be more distributed along the outer space of this chamber, which actually helps you to achieve that the fresh air distribution, which is the unburnt, unreacted gas, which is cold and more dense, is distributed just along the surface in contact with the fuel fume. And the exhaust gas, or the burnt gas, which is very hot, will be centered mostly in this part of the chamber. So you could achieve actually a good distribution of the unburnt gas, which is a fresh gas, in this chamber along the surface of the fuel. So actually, some people they might think, while the turbulence helps with the combustion process, so if we have a stronger turbulence, it would definitely be better for the combustion in a diesel engine, which is not quite true, because that if you have a very strong turbulence, the fuel penetration from the injector will be shortened, definitely, and then the fuel distribution will not be optimized in the chamber. In the outer area of the chamber, there will be much less fuel penetrate till there, and the fuel concentration or the air-fuel ratio will be very low near the center of the chamber. So if the spiral is very low, that definitely is not a good sign for a good combustion, because not a good mixture will form in the chamber. Also, if the turbulence is or the spiral is very low in the chamber, then the penetration of fuel will be very long, and it definitely would reach the side of the cylinder, and it will pass the rain and will contaminate the lube oil in the engine. So the spiral strength should be optimum for individual engine design. And let's see if there's anything else interesting we could talk about here. This is actually the maintenance manual for the Fairbanks Morse submarine engine, and from here you could actually see that exhaust leading here, because this is actually counterclockwise operated engine. So this is exhaust leading shown here, and seems not too much interesting thing here. Just one thing here is that just got another interesting or nice looking nozzle from the Nozzle company for their RTA 84C 2-stroke main engine, and the manual for this thing here, nowadays they are using such kind of a 2-piece nozzle, but in a long period ago they are only using the one piece nozzle, which features a actually this one here is a 1-piece nozzle, and this one here is a 2-piece nozzle. The atomizer is here, which I just showed you, and it's held together with its valve or the spindle body here by just such a bush. And this is a 1-piece nozzle. The atomizer part is heat shrinked into this spindle, or like the valve, the needle valve body. So but definitely this thing cannot be served on board. You need to return it to the workshop for them to replace. If the atomizer is damaged by the warmth from the fuel, they need to pull this thing out and to heat shrink a new atomizer here again. But with a 2-piece design, you can just change individual parts based on their condition. That's just or what I would say in this video, and I would upload several more videos I shoot in the museum maybe a few days later, and see you then. So basically they have 4 Fairbanks Morse opposite piston diesel engines. Here you can see all the meters: revolution, cooler, freshwater cooler also, and let's see, control, upper crankshaft, upper connecting rod, upper piston there, the loop oil pipe for the upper crankshaft main bearings. Okay, injection pump, fuel injector. I'm not sure why they take all the injection pipes off, maybe for the safety reason, and the indicate valve here. So now here you can see the lower crankshaft doors, crankcase doors here. I think this is a charged air temperature gauge, and I think the intake is directly drawn through these silencers into the charger from the engine room. And you can see the piston used in the engines. This special shape, I guess they have double injectors placed here and here. So the combustion chamber is formed by the upper piston and the lower piston here. Very heavy. And the connecting rod. See the main bearings, small end bearings, looks like some copper alloys turn green, and the bigger end bearings, the oil passage here.